we've gone through the zeroth law, and we've done, we've said some very trivial things about the first law. So now let's say something a bit less trivial. So as I said, these laws, you can think about them in various ways. So there are different ways of presenting them, some of them more insightful than others. So let me talk about the physical process version of the first law. Okay, and the first law is written for you over there, minus the part that comes from the Penrose process. Okay, so in this physical process version, so what you want to do, so here you're having some black hole with some horizon, and you want to send some so you want to add some mass to, and maybe angular momentum to the black hole, and you do so by just sending some matter or energy momentum flux through the event horizon in such a way that you start with the stationary solution of mass m and j, and you end up with some other stationary solution with mass m plus delta m and angular momentum j plus delta j, something like that. So let me call T mu nu matter the stress energy of the matter that you're throwing in, and basically for this version of the law, you want to use some we're going to do something very naive. So we're not computing the mass and the angular momentum at infinity like we've done for the first part of the course. Here we're just very naively throwing this guy inside some fixed background. So you want to really think of the increase in mass as due to this energy momentum flux crossing the horizon. Okay, so delta m is going to be the integral from, say, 0 to infinity of the lambda. So lambda is the affine parameter on the horizon times d squared omega. This is the volume element of the cross-sectional, the cross-section into the energy flux of the matter. So since I'm looking at mass, I should be dotting this into, how should I call this? Tau nu. So tau is just d. Yeah, maybe I forgot to say. So my black hole is axisymmetric, stationary axisymmetric. So it has Killing vectors dt and d phi. Okay. And since I'm looking at the increase in energy, so I should be looking at the energy flux, which is T mu nu into dt, which I'm calling tau nu. Okay. And then I basically want to dot this index into the normal to the horizon because it's crossing. And that's just, well, I'm calling it K nu. Sorry, this is, let me style nu and K nu just to keep in agreement with my notes. We used to call this guy L before. So this is the normal to the horizon. But as you well know, this is also tangent to it because the horizon is now. Okay, so is this formula clear? This is what you would have very naively written for the increase in mass if we hadn't done the whole first part of the course. So this should be intuitively very clear. And similarly, you have you have for the angular momentum, you have a similar relation. The lambda, d squared omega T mu nu matter. But now you're using, okay, what did I use? Phi mu. So by this, I just mean d phi, the Killing vector d phi into k. And apparently, to keep conventions clean, I want a minus sign over here. Okay, and now, okay, so these are the things that enter the first law. We also want the change in the area. And the change in the area is, well, integral right. So it's basically, I mean, remember, so yesterday we were talking about the expansion of a congruence of null geodesics, and we defined this theta, and theta was basically a dot over a. Therefore, if I want to get the area, I should be integrating this expansion into a. So I should be getting delta a is equal d squared omega integral d squared omega times basically delta theta, which is the integral over d lambda times theta of lambda. Okay. Yeah, so this basically comes from this definition over here, and I'm integrating it from 0 to infinity. But actually, this is I mean I'm assuming that you know, this process starts at some initial lambda and ends at some finite lambda, so it's not going to like be stretched over the entire range of lambdas. Okay, very good. So now we want to manipulate this relation. And we can do some trivial integration by parts here to write this as d squared omega times so we're writing this as d of lambda theta. So I'm getting lambda times theta from, if you want, 0 to infinity. And then minus integral d squared omega times lambda d theta d lambda. Sorry, lambda d theta. Sorry, I messed it up. Okay. And the point is that this thing is 0. The reason that it's 0 is that both before this matter flux comes in and after, we're assuming stationarity. The horizon is a Killing horizon, and on the Killing horizon, the expansion is 0. So yeah. Right. Okay. So this term is 0, and then we only have to massage this term. And this term, we can massage it further to write it as d theta by d lambda times d lambda. But d theta by d lambda, if you remember from yesterday, had some formula in terms of the Chaudhuri equation, which is minus a half theta squared, and then there was sigma squared, and then importantly, there was this term r mu nu, k mu, k nu. Okay. So now what we want to assume that even when it's non-zero, theta is going to be small. And this guy is also going to be small. So we can just approximate d theta by d lambda to be minus r mu nu k mu k nu. So this is going to be d squared omega lambda times d lambda times r mu nu k mu k nu. So using Ray-Choudhury's equation. And now what we want to do is to use Einstein's equation and replace this guy by, T mu nu. Okay, so now we're going to replace this guy using Einstein equation by 8 pi g T mu nu plus some terms that are proportional to g mu nu, but these terms are not going to contribute because k is null. So we just forget it. T mu nu matter. Okay, so the whole thing is 8 pi g integral of d squared omega d lambda T mu nu matter into lambda k mu into k nu. But now all this, okay, so is it clear up to here what we did? So we just use Ray-Choudhury, and then we use the Einstein equations, and then we're able to massage this. But now remember that along the horizon, the Killing vector, so this is something that we derived today. Xi mu was something like lambda k times k mu, which we're calling L mu earlier in the lecture, right? Therefore, this term over here is nothing but 1 over k Xi mu. Where Xi mu is the Killing vector that's orthogonal to the horizon, that particular one. Okay, which in our case, since this is a rotating black hole, it's going to be given by this. Okay, very good. So now I want to write k over 8 pi g times delta A is equal to, integral d2 omega d lambda T mu nu matter times. So I said the Xi mu is that guy. So in my notation on this board, that's tau mu plus omega h phi mu into k nu. But this is nothing but delta m minus, because of my convention, omega h delta g. Okay, so what I guess is nice about this derivation is that you see physically exactly what happens. So you're throwing in a little bit of matter and the horizon distorts a bit, and then its area changes in such a way that this thing is satisfied. And essentially you're using Einstein's equations here to pass from this geometrical object to that's connected to the change in the area, to this dynamical object, which is the matter that falls in, and you just get the first law. I should say that exactly just a simple variation on this argument can be used to also show the second law, that the area always increases. Can somebody pinpoint where how that might go? Yeah. Can anybody stare at this board and see how one may come up with an argument that shows that the area always increases? Very good. So if you look at this, then you see that you have this term over here, and then if you use the Einstein equation and you're imposing that the matter satisfies the null energy condition, which basically implies that this term is positive, then you basically get that the fact that the area of the event horizon can only increase. Okay. So so this is very good. So okay, so the point is that this looks like the first law of thermodynamics, where this okay, this nicely this one is the same thing. This is energy, and this guy looks like an entropy, and this guy looks like a temperature. Okay, very good. So this is the physical process version of the first law. Now we're going to do yet another way of deriving this first law relation, which is going to use the full power of the covariant void space formalism, which I'm sure you're missing. So okay, but what's okay? What's the difference between the derivation? So here you had to assume that the perturbation is stationary, whereas but you don't need to assume that that you're close to the bifurcation surface. You don't really need this could be a black hole from collapse. And what we're gonna do, we're not gonna need to assume that the perturbation is stationary, which is nice. It just has to be on shell. However, we're gonna need to talk about the bifurcation surface. So that's not exactly a black hole in nature. But okay, very good. So so that's one thing. Any questions about this before I move on to like hardcore formalism? Okay. So I think that the main interest of this other, so this is I mean there are a couple of papers, you can just find them. There are GRQC what 9403-028 and 93-070 sorry 028 and this is 38 something like that. So the main interest of this derivation is that now you're not constrained to do Einstein gravity. You can actually try to study what happens to this first law in an arbitrary theory of gravity, including higher curvature corrections and so on. And as you're gonna see, this formalism is super powerful, and it's actually spitting out a quantity that that plays the role of you know, the good thing on the right on the left hand side of this equation that could satisfy the first law relation. So point being, the horizon area is the thing that enters on the left hand side only when you're in pure Einstein gravity or Einstein gravity plus matter. If you're doing some weird theories of gravity with non-trivial curvature couplings and so on, this formula will get modified. And doing this formalism is going to tell you exactly how you have to modify it. Okay, so now we have the motivation to actually go through the formalism. So we're using the covariant phase space formalism. So we're taking any theory of gravity. And actually we have any asymptotics. Can be flat, ADS, whatever. I mean, you just need to make sense of your boundary conditions of your spacetime such that you can get finite integrable conserved charges. But otherwise, as long as you can do it for your theory in your spacetime, this will work by definition. And you want to start, so you want to start with the stationary black hole background. So background, which I'm gonna call phi. So phi is basically the metric, but it can be, you can have a zillion other, I mean, I'm not sure you can have a zillion other fields, but okay, this is going to be the background, and you have a killing vector xc. Therefore, the xc of phi is 0. Okay, and then you also want to consider an arbitrary on-shell perturbation of phi, which I'm going to call d phi, which is on-shell. But as you see, now it's not restricted to be stationary anymore. It just has to be on-shell. Okay. So now, if you remember from like 2 weeks ago, one can come up with some way of constructing conserved charges in terms of these d-2 forms that one integrates at infinity. And the expression for the thing that had to be integrated, there was this kc, which depends on phi and d phi, which look like delta of qc minus c of theta of d phi. And this q was d of this q was basically the difference between the usual Noether current and the on-shell vanishing Noether current. So there was an algorithmic procedure to construct this guy. And this extra term, we picked it up when we wanted to get a nice equation for decay. So we wanted to see that k is conserved whenever certain conditions are satisfied. And so we had to, we were able to get this nice condition that the symplectic form on dxc phi, d phi plus dk So if you remember, we got this equation, and then we said whenever xc is a killing vector, this guy vanishes. Therefore, k is closed, and that leads to conservation. We either had asymptotic conservation when this guy was just an asymptotic killing vector, so omega would just go to 0 at infinity, but would not in general be 0. Or if it's an exact killing vector, which is our assumption over here, omega is 0 everywhere. Therefore, decay. So not only is it conserved by doing the game at infinity, but it's you can also evaluate it on any radial slice. Okay. So that being said, let's actually evaluate it. So I'm looking at the t equal to 0 slice, if you want. So this is my black hole. So basically, I want to look actually at a constant time slice that includes the bifurcation surface. Okay. So here is my B. Maybe so if I'm drawing my black hole, whatever. So basically, I want sigma to be this time slice over here that connects B to say I0 in this case. Okay. Or I could be asymptotically ADS. Case in which I would be doing this, but okay, it doesn't matter. So this spatial slice includes sort of goes to the bifurcation surface. So I have something like this. So this I'm going to call this sigma infinity, and this is B. So if I integrate this equation over sigma, so sigma again is this integral dB dkxc on sigma is integral over the boundary of sigma of kxc. And the boundary of sigma consists of two pieces. There's the piece at infinity. So there's sigma infinity of kxc. And then there's the piece at the horizon, which, as I said, I'm evaluating it at the bifurcation surface. which comes with a minus sign because of orientation issues. So it's the integral over B of kc. And this is 0 because dk is 0. Okay. And now the point is that this is what we call the, I think we called it delta slash of xc or something like that. So the integral of kc over the sphere at infinity, it gives you the infinitesimal, the difference in charge between two infinitesimally close backgrounds. And the d slash means that that's not necessarily integrable, so you have to be careful, something like that. Okay, so this is the charge that you measure at infinity, and all of this is saying is that you're going to get the same thing by evaluating this kc at the horizon. Okay, now the expression for kc is generally given by this. And you see that if I'm actually at the bifurcation surface, what is C at the bifurcation surface? Zero. Very good. So we just discussed this. When you have a bifurcate killing horizon, C actually vanishes at the bifurcation point. Okay. So so how should I write this? I just don't like my notation. Let me call this delta QC, but this is very bad notation again. Okay, let me call it this, although I don't like it. Okay, very good. So so very good. So what are we getting? So we're getting that the integral of kc over the surface at infinity, which using the fact that c is this particular killing vector, as we have seen previously. So this is going to be basically delta h dt plus omega h and delta h d phi. It is clear. So the charges are basically linear in the killing vector. So I'm just going to get this particular linear combination of the charges associated to dt and d phi. And this is nothing but, delta m minus omega h delta j by definition. And this thing is going to be equal to the guy at the horizon. So it's going to be equal to integral of delta qc over the bifurcation surface. So basically what we want to do now, so this is already the right-hand side of the first law. So what we want to do, we want to massage this horizon piece. So we've already seen that just this Noether charge and the fact that we have an exact killing vector of the background, it's telling us that this contribution is just something intrinsic to the horizon. Okay, it's basically the Noether charge evaluated at the horizon, the Noether charge associated to this C. And now we want to massage it to put it in something that looks like the left-hand side of this equation. So how are we going to massage it? Well, we basically have to evaluate it. So let's try to evaluate it, say, in Einstein gravity, where we know what we're doing. So Einstein gravity. the QC that enters over here, we actually computed it. It's minus 1/16 pi g d mu xi nu minus d nu xi mu into epsilon mu nu and then alpha 1, so alpha d minus 2 dx alpha 1 which dx alpha d minus 2 times or divided by 2 times d minus 2 factorial, something like that. Okay, so I'm asking you to remember that we actually did this exercise like 2 weeks ago. And of course you don't remember, but I'm telling you that it's true. So we did the whole spiel with the varying the Einstein equations and the Onshel vanishing notor current, the notor current, and and this is what we got. This is known as the Comart term. Okay, so but this is the expression for the charge in Einstein gravity, so that's very nice. Okay, very good, but we want to massage it a little bit. So we're basically sitting, because you see the thing that sits there on the left hand side, it's not a total variation, it's k times delta of something. So we need to get that structure. And the point is that on the bifurcation surface, so here where you have xi mu equal to 0, you have d mu xi nu is k times epsilon mu nu, where this guy is called the binormal. Okay, so xi is 0, but of course its derivative doesn't need to vanish. Its derivative is antisymmetric. Is it obvious? It's the killing vector, so it's antisymmetric in the two indices. So this binormal is something that's antisymmetric, and it has the property that for any t mu which is tangent to B, to the bifurcation surface, you have t mu epsilon mu nu equal to 0. Okay. So and also this epsilon mu nu is normalized. I think it's normalized to -2 or something like that. Did I write it somewhere? I didn't, but I think it's true. Okay. So this guy is normalized to -2. Very good. Otherwise, we wouldn't make any sense of this equation. Okay, very good. So now we want to show that this equation is true. So in order to show that, you just dot this quantity into t mu. But if you dot it into t mu, so you immediately get it. It's 0 because xi mu is 0 on all of the bifurcation surface. So if you take its tangential derivative to the surface, you still get 0. Okay. So since both of these quantities dotted into t mu are 0 for any t mu, then they must be proportional to each other. And then you do some song and dance and convince yourself that the proportionality constant is this k. Okay, very good. So therefore, now you're going back to your charge, and then you're getting a 2k epsilon mu nu from here. And then you use the fact, okay, let me erase a little bit because otherwise we can't do anything. And then you use the fact that this guy is normalized to, I really wish it is normalized to -2. Okay, very good. So you have this. Okay, so then you're basically contract. So then what you're doing over here, you're basically choosing your indices. You're choosing mu and nu to basically coincide with these two guys. I mean, you know, in the Schwarzschild black holes, the two guys that you're gonna get from this equation are going to be T and R. So you're going to split your indices over here into the ones that that actually contract nicely with the binormal and the ones that are perpendicular to it. And these guys are just going to give you the volume form on the bifurcation surface. So d-2 dimensional thing. And these guys just give you a -2. So let's try to do the calculation. There's a 2, there's another 2, and there's another 2, and the -1 over 8 pi g. Actually, there's k over 8 pi g into the volume form of B. Very good. And this is a great success because now you see that the integral of QC over the horizon is just going to give you k over 8 pi g into the area of the bifurcation surface, which is almost, except for the delta, is exactly what you find on the left-hand side, including all the factors. Okay. However, in order to do this properly, you need to get the delta. So you need to get the fact that the delta sits in front of this guy and not of this guy. And then there's some song and dance. So the way that you can show that is by looking at the, so basically you can show the delta of d mu xi nu is 0 on B. So part of this, so the variation of the killing vector is 0 because you're not changing the killing vector as you're sending in stuff. And also, so there's a part that involves the variation of the Christoffel symbol, but that's dotted into Xi. And since you're on B, Xi is 0, so that's also 0. So then you basically keep on massaging this equation until you convince yourself that this equation is still true. So delta of this guy is equal to delta of this guy. And that's it. Because, okay. So what's happening? When you hit, yeah. So basically this massaging is telling you that you can still replace the mu this antisymmetric combination by epsilon mu nu, even if you're inside the variation. Okay. And once you do that, then the calculation goes through immediately, where k is a constant, and what you're picking up is the delta of the volume of B. Was it? I know I didn't do it, but was it clear more or less what I was saying? Okay. Very good. So basically the point is that delta of this equation is still true. So when you act with a delta over here, you can just write it as k times delta epsilon, and then you have the delta going there, and then you massage it, and the deltas on these epsilons cancel. You still get your -2, and then the only part that remains is the delta that acts on the perpendicular. Okay. So this is how you get back the the first law in Einstein gravity from this formalism. But the nice thing that is that this formalism is very general. So one really wants to get the full the full result and not do just Einstein gravity, but actually get a formula for the entropy in a general theory. Okay, but okay, this is how we get it. So we're going to do basically the same thing, but now we're going to have to be careful about what exactly this QC is in an arbitrary theory of gravity. That's a bit the idea. Okay, so sorry. So what I wanted to say is that this basically implies that k over 8 pi g delta AH, sorry, is equal to k over 8 pi g delta H. And as I said, already for Einstein gravity, this is slightly different from the physical process version. In that you're not restricted to be stationary, but you're evaluating at the bifurcation surface. Okay, so now we want to consider the theories with higher derivatives. So we consider some totally general Lagrangian that depends on G mu nu, the Riemann tensor, and all sorts of matter fields, their covariant derivatives, arbitrary numbers of covariant derivatives, matter fields, etc. Actually, you can also consider theories where you have covariant derivatives of the Riemann tensor appearing in the Lagrangian, but then we have to work even more to get an expression for the entropy. So I won't do it, but it's done in one of these two papers. So I mean, one can in principle get an arbitrary expression. So so basically, the what Wald and I prove is this QC, which is the D-2 form, which will ultimately enter this contribution from the bifurcation surface, is given by some contribution which depends on your fields times, so some contribution that's proportional to the Killing vector. Remember that these are D-2 forms, so you have a whole lot. There are tons of other indices floating around, but I'm just showing some particular ones. Plus a term which is x mu nu d mu xi nu, plus some ambiguities that we discussed, phi, LC, phi, sorry, I'm calling it delta xi phi, plus dz. These guys I don't care about because this integrates to 0, and well, here basically the form of this guy can be absorbed in the other. I guess that's the idea. So okay, so let's forget about it. Okay, and the whole like the important point. So you see that this term you don't really care about because it's 0 on the bifurcation surface. So basically the only term that you care about is this. I mean, we've just computed it. You see, we've just computed the x mu nu in Einstein gravity. It was indeed proportional to the antisymmetrized covariant derivative of xi nu. Here you just had some epsilon tensor, but in general it's gonna be a complicated thing, and they claim that x mu nu, and then it's a D-2 form, so it's alpha 1 through alpha D-2. Is going to be minus ER mu nu rho sigma epsilon rho sigma alpha 1 through alpha D-2, where this ER, basically, let me just write it actually. It's the variation of the Lagrangian with respect to the Riemann tensor. So R mu nu rho sigma done as if the Riemann tensor were an independent field. Okay, so of course normally the Riemann tensor is constructed from the matrix. So when you vary the Lagrangian, you just vary the metric, and then this guy has a complicated variation. This is not what you're doing here. You're just taking the derivative of the Lagrangian with respect to the Riemann as if Riemann were an independent field. This is what giving you this term x mu. So in the case of Einstein gravity, where the Lagrangian is just proportional to the Ricci scalar, you see this thing is just going to give you some antisymmetrized factors of the metric, right? Are people following? Is this trivial or? So if L is R, which is then you can write this as R mu nu rho sigma G mu rho G mu sigma, something like that. So when you do this, you're just picking some anti-symmetrized combination of these G's, which at the end of the day is going to give you this X mu nu, which is basically proportional to the volume form. Okay. Maybe I should close this. Okay, very good. So, so now we want to prove. Let me sketch how the proof goes. Because you see, once we do this, basically this is going to be the main term that's going to be contributing to this B integral, because this guy vanishes. So this is the main contribution. So let me just sketch how you do this, which is a complete pain. So the way that you do this, you just derive what this QC is the usual way. So to do it, you have to look at the variation of the Lagrangian, which is equations of motion into d phi plus d theta. We do that because we want to compute d theta. And basically, the point, so the way that we're doing this, so basically, in order to get the equations of motion from the variation, we had to integrate by parts and put all those boundary terms into theta. This is how we're finding out what theta was. And the point is that this theta goes like 2. So he's calling this thing E, right? I think equation of motion with respect to the Riemann. I think this is what it's supposed to mean, mu nu rho sigma. So they're claiming that this is 2 oh God. Lambda. No, okay, sorry, never mind. What is going on here? So this is 2 times dl by dr alpha mu nu lambda d lambda delta g mu nu plus terms with no derivatives on delta g mu. Okay, so what are we doing over here? Basically, yeah, I guess I could use that board. So basically, what you want to do, so as I said, this is trivial. You just want to put all the, when you integrate by parts, you want to collect all the derivative terms. So delta L, of course, it's dl by delta g mu nu times delta g mu nu plus delta L by delta r mu nu rho sigma delta r mu nu rho sigma, where of course now you have to write it in terms of delta g because you're deriving the equations for the metric, the equations of motion for the metric, plus some other crap. So all the matter fields, of course, because you also need plus matter variations and so on. So now, so here delta r is not varied independently. Of course, we're just getting the Einstein equations. So now you need to write what this thing is, and this delta r is basically going to contain 2 derivatives on the metric, 2 covariant derivatives on the variation of the metric by the definition of the Riemann tensor. And I'm sure you guys cannot see anything over here, but this is going to look like d mu d sigma delta g nu rho, and then plus some other term which is actually proportional to delta g rho sigma. So the other term is just going to go straight into here. So we don't care. But you see, when you pick up this term, you want to integrate it by parts twice in order to construct your Einstein equation. And when you do that, you're going to pick up something inside d theta, which is d mu theta mu. And the claim is that what you're picking up is precisely this. Right? So you integrate by parts once, you get d mu of this thing. And then the second term doesn't matter because do you see what I'm doing? I'm doing E right. So there's the whole coefficient times d mu of d sigma delta G. So I'm writing this as d mu of E right d sigma delta G minus d mu E right d sigma delta G. So this term is going to be precisely this term here that I care about. And this other term, I can integrate it by part once, but it's going to go into here because it's just going to be proportional to delta G once I take out. And the rest, of course, the two derivatives on ER, they're just going to go into the equation of motion. I don't care. But this is the term that I care about. So this is the most number of derivatives, covariant derivatives that I'm getting on delta G. That's sort of the point, and everything else is just proportional to delta G. Now, in order to construct, okay, so where was I? Okay. Okay, so just to write this nicely, so theta is equal to 2. So they're calling this thing ER because this has you see, my God, I hate this. Epsilon alpha 1 to alpha d minus 1. So of course theta is a d minus 1 form. So the way that I'm getting this is that so I have an extra epsilon that comes from the fact that my L was a D form. And then so I'm having d minus 1 free indices, and the last index is contracted to the index from here, something like that. And they're calling this quantity ER mu nu lambda. It's not the same as this. It's slightly different because I'm contracting one of the indices with the index from epsilon. I mean, yet again, it's not that you're going to follow every step because then we're going to sit here forever. So, but that's basically the idea. So you're getting that this theta. Where was it? This theta is 2 ER nu rho sigma. And then remember there's all these other d minus 1 indices that are floating around. D sigma delta G nu rho plus things that are proportional to delta G min. Okay. Now, if you remember when we were constructing the Noether current, so the Noether current was theta of delta xi phi minus the boundary term that we get in the variation, which was xi dot L. Which was equal to minus the on-shell vanishing Noether current plus dqxc. So this is how we get dqxc. And the point over here is that when you're extracting qxc, of course, everything conspires for these guys to be exact. And the main point is that when you're getting this qxc, you're just going to get rid of one of the derivatives. Okay, so here, okay, so of course here, because you have theta evaluated at the you know, on the Lie derivative of the metric with respect to xi, this thing is just going to be d nu xi rho plus d rho xi mu. Okay, so now you're getting two derivatives on xi, but when you're like constructing this q, you're going to get rid of one of the derivatives. So at the end of the day, Q is just going to have at most one covariant derivative acting on xi. And they're claiming that you can put it in this form. The reason that you can put it in this form is sorry. It's simple. So in the case of killing vectors, it's very simple. So we saw that d mu xi lambda was some r mu nu lambda rho xi rho. Some, well, I forgot exactly what it was, but it was actually proportional to xi. So then you don't care. So you can always make. The point is that you can always make the linear term be antisymmetric in this derivative. Okay, but the point of actually going through the exercise is to get the coefficient of this d mu xi nu, which you see from here is going to be given by this 2e, right? Because you're just getting rid of one derivative. And if you're doing the algebra correctly, which I'm definitely not, then you're basically getting this. Okay. So again, I was just sketching the steps, but just for you to, I hope it's clear how they get this. It's a very painful calculation, and you have to keep track of like about a zillion indices. But at the end of the day, this is the main idea. You're just like you know, painfully just moving covariant derivatives and painfully constructing the charges, and you're just looking at terms that have the maximum number of derivatives they can possibly have on this xi, and you get that the maximum derivative number of derivatives is 1, and the coefficient is well determined. It's basically the variation of the Lagrangian with respect to the Riemann, varied as if the Riemann were an independent field. That's all there is. Okay, so this is where it comes from. And now, very good. Okay, so now we can look at the first law. So in order to, so as I already explained, so the right hand side of the equation is given by the, oh yeah, it's over here. So the right hand side of the equation is just this term, which was just delta m minus omega delta j by definition. So this will always work. So we just need to evaluate this guy. And this guy is, so the integral over b of kxc of delta phi and phi. So it's integral over b of xi mu. So now, of course, I have to take the variation of this charge, because this is what enters in the formula for k. But the xi itself doesn't vary. So I'm just pulling it out. So it's xi mu delta w mu plus delta of x mu nu d mu xi nu minus xi dot theta. And as I already explained, since I'm on the bifurcation surface, these two terms drop out. And I'm left with this. And as I also already explained in the case of Einstein gravity, so when you're writing the antisymmetrized derivative of xi on the bifurcation surface in terms of the binormal, that thing actually, that relation, so when you write this in terms of k epsilon mu nu, where epsilon mu nu is the binormal, that thing is, it's still valid in presence of the variation. So you're just pulling this, you just end up pulling this delta out, sorry, the k out. So you're having something like k, where is it? Where is it? K times the integral over b of delta x mu nu epsilon mu. And be careful that this guy is actually a d minus 2 form. Okay. And now basically what Wald wants to do, he wants to define. So now we're going to define the following quantity SW, which is 2 pi integral over B minus dl by d r mu nu rho sigma into epsilon mu nu epsilon rho sigma times the volume of B. So this is basically taking care of so this is basically plugging in the formula that we had for xi mu, and then taking care of all this epsilon. So the vol B is it comes from the perpendicular guys. So you're gonna write this as a binormal into some perpendicular guys. The perpendicular guys are giving you the volume form on B. This binormal is this guy over here. And the second binormal just comes from this epsilon mu nu here. Okay. So this is a definition. It's called the Wald entropy. And the point is that by construction, it has the property that delta m minus omega h delta j is not equal to this, but it's equal to k over 2 pi delta S Wald. Okay, so basically I've said what I've done. I said this is, can I get these things right? 1 over 2 pi S. Well, after putting in the integral, so I exchange the delta with the integral. Okay. Okay, so what does this mean? It means that in any like arbitrary theory of higher derivative gravity, whatever you might want to do, and you can generalize this also when you have derivatives of the Riemann and anything that you want to do, there is some quantity. This quantity has a nice physical interpretation. It's basically the neutral charge in this covariant phase space formalism that's evaluated on the bifurcation surface. And this thing satisfies, you can prove using on-shellness, so using Einstein equation, that it satisfies a relationship of this kind, where k is the surface gravity outside. So this looks like the first law of thermodynamics, with the analogy being again this is the temperature, and this is some sort of entropy. This entropy is not the area of a 4G Newton, which is what you get in Einstein gravity, but it's given by this general formula, and you just compute it and you find out what it is. But the point is that structurally, in any theory of gravity, you always have a law like this, which is very nice because a priori it wasn't clear. Okay, you prove it for Einstein gravity, but how do you know that other theories might do it? So this is a very, very general proof of that. And so in string theory, where you actually have a sort of, in string theory, you do have some sort of microscopic description of these black holes that sometimes in rare supersymmetric occasions, you might know exactly what it is. And then, you might have some sort of leading formula, say at large charge. So large charge means large event horizon. And then, the leading contribution to the entropy is captured by the area term. But then you have subleading contributions, which come from the R² corrections to the string action and whatever, and you can just compute them and match them to the microscopic result if you have it. And then in nice occasions, and so for example, Atish Dabolkar has worked out a lot of this precision matching of black hole entropy and compute all these R² terms, and they match precisely. It's very nice, but the gravity quantity that you use as a proxy for what entropy should be is this guy, it's the Wald entropy. So, but this is why it's important to have derived it in this very general way, that it shows that there always exists such a function, and this is the correct function because it precisely matches the the number that string theory is spitting out at you in these examples. Okay, very good. So if you want, I can give you an exercise, which for once I'm not gonna do. Like you can just, so if you want to see how this works, you can just compute. I mean, maybe you can verify first law in Einstein, Gauss-Bonnet, gravity in D equal to 4 and 5 for, say, a Schwarzschild black hole. So your Lagrangian is basically R over 16 pi G plus some alpha times the Gauss-Bonnet term, which is R mu nu rho sigma minus 4. I'm scribbling it because I'm assuming you know what it is, but if you don't scream, because this is not readable, but anyways, it's 4 R mu nu plus R squared. Okay. So take this Lagrangian, you look at the black hole solutions in 4 dimensions, it should be the same. But then you compute the conserved charges. They don't have to be the same. Compute the area. And you verify the first one. Okay, very good. So so now we're done with the first law. So I've showed you like 3 different ways of checking it in all possible manners, and also I talked about this matching in string theory. So so this really looks like very much like the first law of thermodynamics. And of course, I'm talking in a very imprecise way because this is I mean, all that we've done is just some analogy, right? We're just looking at mechanics of like geometric properties of the black hole and how it responds to throwing in matter and so on. But we haven't shown that this thing is an entropy. It's just some quantity that for mechanical reasons it behaves like this. But we haven't shown that it's an entropy. And actually, it's nice to note. So there was this paper in 73 by Bardeen, Carter, and Hawking on the 4 laws of black hole mechanics. And they note this nice analogy and so on. But however, in the discussion, they say very, very explicitly that it should, however, be emphasized that, K, the surface gravity, and A are distinct from the temperature and entropy of the black hole. Because as you well know, the temperature of a black hole is exactly 0. The thing just absorbs and doesn't emit. So this is all like some mathematical analogy and with no physical meaning. This is how they ended their paper. Of course, I guess just a year later, Hawking showed that actually, if you include quantum effects, then black holes actually do radiate and they do have a temperature, and then it's at that point that so I want to write this K over 2 pi delta AH of 4G. So the important thing is that the temperature has this and the area has that. So this is the entropy and this is the temperature. And once he showed that there's an actual physical temperature that's associated to the horizon, then it became very clear that these were not just some random analogy, but these were actually the laws of thermodynamics as applied to black holes, and they should be taken seriously. Okay, very good. So I'm done with the first law. Now we can go on discussing the second law. The only problem is that I'm losing my voice. But are there any questions about this? Everything crystal clear. Everything is just some disgusting calculation that in principle you're understanding how to do, but we're not doing it because I think that's the main message of this course. But I told you where to find it. If you're really interested, you just go and read the paper. It's technical, but it's not that complicated. Okay, very good. So now we know how to compute the entropy in full generality. And now let's discuss the second law. Actually, so the second law, it says that, well, there's the second law for the horizon itself, which basically says that in any classical process, the area of the event horizon increases. So when we discuss the physical process version, we already saw that. It just follows from the condition that you impose on matter. It's a classical condition that it should satisfy the weak energy condition. So that we saw. There's another derivation of it, which is along the lines of what we did in the first lecture. So basically, the change in the area is related to the expansion of the horizon generators, this theta, and you can basically show that theta has to be greater or equal than 0. The reason is that if theta were negative at some point on the horizon, then you can use Raychaud-Douris equation and the weak energy condition to show that theta needs to go to -infinity within finite affine parameter. And then you're going to run into a problem. So as we discussed, when theta was going to -infinity, that could be either a focal point or a singularity, an actual singularity. In the case of the horizon, it cannot be a focal point because of the very definition of the horizon as the boundary of the causal past of future null infinity. So being the boundary of some causal part, it has to be contain only prompt null geodesics, which cannot have focal points. So the thing cannot be a focal point. And then you're left with a singularity on the horizon as your second option. You don't want that either. Therefore, you conclude that the expansion has to be positive everywhere on the horizon, positive or 0, which implies that the area always increases. So that's roughly the argument. And this is nice. So this sounds like the area is something analogous to an entropy, and that's all very nice. You can play other games. So I told you 2 ways to see that it increases. Another thing that you can do, you can just take 2 black holes and merge them and show that the area of the horizon of the final black hole is going to be greater than the sum of the areas. That's a trivial exercise. I'll let you do it. And I think something that people really appreciated at the time was the fact that the area also always increases in the Penrose process. So you extract energy, but yet there's a limit to energy extraction, and the limit is such that the area of the horizon of the curved black hole is still increasing in the process. So there's another convincing piece of evidence. Okay. But I mean, this is all okay. So this is so far for the analogy. As for the actual meaning of area as entropy, of course, the problem is the fact that that you have this property of black hole uniqueness. So it was very it's somehow very surprising that you can take all these like complicated collapsing stars and collapse them, and the final state is this thing that's characterized by 1 or 2 parameters. So that's basically 0 entropy for all practical purposes. And the problem with that is that now if you take your cup of tea and you throw it inside the horizon, you're just changing 1 parameter. So all the degrees of freedom, all the entropy of that hot cup, I mean, it really looks like you're losing entropy from the observable world. And there are some people who are very bothered by that idea. So among them was Wheeler, who was apparently a star figure at Princeton in the late 60s. And he basically gave as a problem to his student Bekenstein to try to figure out what this entropy business was. So how do you make sense of this apparent violation, or how to say, impossibility to verify the second law of thermodynamics in the presence of black holes? And so actually there's, so I think Bekenstein died just a few years ago, and there was a memorial volume in his honor. So there are a lot of nice historical, historical recollection articles about it. So in particular, Wald wrote one. Wald was a PhD student at the same time as Bekenstein in Princeton, and he wrote some very funny things about what he thought about Bekenstein's project. So I'll just read. Okay, so actually they're discussing. So Wheeler told Bekenstein to look at this, and then he discusses how Christodoulou had just shown that this irreducible mass, which is basically the area of the event horizon, always increases even in Penrose process. So it sounded like it was natural to somehow relate the concept of entropy to this area because it was always increasing. However, Wald, at the time, I felt that this was an utterly ridiculous project to work on. First, as already mentioned, I was not troubled by the apparent transcendence of the second law of thermodynamics. So this is the thing that it becomes practically unverifiable experimentally. Second, the analogy between the second law and the area theorem seemed extremely artificial. It seemed quite unnatural to me to try to marry a statistical law with a mathematical theorem. But most importantly, in the absence of a fully developed quantum theory of gravity, what could one possibly show, or how could one possibly argue for the validity of any highly speculative ideas on black hole entropy that one may propose? I have a distinct memory of leaving a group meeting of Wheeler and all his students shortly after Bekenstein has started working on this project, and seeing Bekenstein and Wheeler stay behind to talk further about the second law ideas. The thought that flashed through my mind at the time was, boy, am I glad I have some good problems to work on. So, I mean, it's really amazing that this thing has worked and has given such. I mean, the area, of course, it's behind holography. Holography basically follows, morally speaking, from the area law that was so successful. But at the time, you have to understand this may look totally crackpot to some people. Okay, so this is why I read it. I thought it was funny. So Wald is a pretty serious person, so I don't want to say anything imprecise. Okay, very good. So Bekenstein was given this project to make sense of the second law of thermodynamics in presence of black holes. So he came up with some proposal, which is the generalized second law. So of course, if you have matter, also matter contributes to the entropy. So he proposed that the generalized entropy, which is defined as the entropy of the outside matter plus some proportionality constant times the area of the event horizon over GH bar. This is sort of the natural thing implied to you by dimensional analysis, because this is the Planck length squared. Increases in any physical process. Okay, so very good. So of course, you guys have certainly heard about the Hawking evaporation process, where the area law is violated of the event horizon decreases. Can people tell me how is that consistent with the area increase theorem that I just gave you? Right. So this is how the generalized second law is saved, indeed, that this guy decreases, but this guy, which is the entropy of the Hawking quanta, is actually large, and actually the full thing increases. So that's correct. But I'm asking you, how is the fact that the area of the event horizon How does the fact that the area of the event horizon decreases, how is it consistent with what I just told you about all these theorems about the fact that it always has to increase? So we derived it from Raychaudhuri's equation plus, how is that consistent? Exactly. So in our derivation, we assumed the weak energy condition, which is something that's satisfied for classical fields, but is not satisfied quantum mechanically. So in quantum mechanics, you can easily find states that violate this weak energy condition. So there's no problem with that. And basically, since the Hawking evaporation process is it's a very much of a quantum process, the weak energy condition gets violated, and this is how you get the area to decrease. But as you're saying, indeed, the point is that this thing is actually increasing, the generalized entropy. Very good. So this is all very nice. However, I guess if you think about it for a little bit, the fact that this always increases in any physical process actually has some sort of funny implications. So since they were doing thermodynamics, so they were kept on playing with like trying to lower various things inside the black hole horizon and talking about work and all that thermodynamic stuff. So basically you see that if you're having the black hole horizon over here and you're just coming with some mass from infinity, so you have a thread and you're just lowering very slowly this mass all the way up to the horizon, right? And then you're just dropping it in. So this has some mass, and of course it has some entropy. Then, because the guy is just hovering above the horizon, the change in energy at infinity from it being dropped in from just above the horizon, it's pretty much zero, right? Because it was already highly redshifted. However, and since the change in mass is very small, and the area of the event horizon only cares about the mass of the thing that you've put in, the final entropy is, say, close to zero, whereas the initial entropy is just S of the matter that you've put in. Okay, so this sort of situation sounds a little bit bad, that you might actually be able to violate this generalized second law by just lowering the things very then up to the horizon. They have some non-trivial entropy, and then you drop them in, and then it seems that you're going to have a final entropy, generalized entropy, that's smaller than your initial one, right? So this is this situation. This is my initial entropy, and the final guy corresponds to the masses behind the horizon, so I don't see it anymore. Okay. And okay, then you might say, okay, maybe the fact that this change in the entropy is zero is not quite correct, because I have to be a lot more careful that I cannot arbitrarily put it as close to the horizon as possible, because objects have a finite size, and then even if I have a very tiny bit of change in the area, this guy gets divided by the Planck length squared, which is an incredibly tiny thing. So, the finite size of my object, I have to be careful about it, because it might actually give a finite contribution. So that's indeed true. But at the end of the day, you still see that even if this contribution is finite, this is a contribution that depends on the mass and size of the object. Whereas this, the initial entropy, is something that depends on its entropy. So you get to the very funny conclusion that in order for the generalized second law to be obeyed, you need some sort of relationship between the mass and size of the object and its entropy. Some inequality between those things. Otherwise, you cannot be satisfying the generalized second law. Okay, so now let's just try to estimate a little bit better what this as finally, so basically the increase in the mass of the black hole due to our dropping out the object. So basically you want to consider that the object has some finite size r. So you're dropping it from this height, and let's suppose you're in the Schwarzschild space-time. So there's some sort of associated Schwarzschild coordinate. So this r is sort of the proper size of the object. So in terms of the Schwarzschild r is given as an integral from the horizon to r of r, which we're trying to determine, of dr over square root of 1 minus 2gm over r. And this thing is approximately 2 square root of 2gm times r of r minus 2gm. Something like that. And you're assuming that this thing is very small. Yeah, so you've basically assumed that this is small. Otherwise, I think you wouldn't have gotten this. But anyways, this is a trivial integral to do. So at the end of the day, you find that the value of the Schwarzschild coordinate at this r minus the radius of the horizon is what is it? 1 over, yeah, it's r squared over 8 gm. Okay. Then, if you want to compute the change in the mass of the black hole, you have to compute the change in energy at infinity. And that's the sort of the local energy of the thing times the redshift factor. And the redshift factor is basically given by this thing evaluated here. So that's okay, let me do it. 1 minus 2gm. Okay, sorry, RH minus R squared. Sorry, let me do it like this. R squared over 8gm divided by R horizon, which is 2g. And sorry, there's a square root, which is important. Yeah, because I have to be, right? I have to be multiplying by the norm of the dt killing vector at the horizon, which is square root of GTT, square root of minus GTT. Okay. So at the end of the day, I'm just getting E times R over 4gm, which is basically the delta M. Okay, very good. So now if I want to compute the S final, then, well, I just need to, since I just have the slightly bigger black hole, I just have to plug this into that formula. So that's eta. Well, actually, we know what this is. It's 1 over for G H bar times no, how do I write it? Delta S final. Okay, I want to write delta S black hole. Okay, let's just look at the variation in the black hole entropy. So that's 1/4 G H bar times delta of the area of the event horizon, which is 4 pi times 2gm squared, and I have to take a delta. So this is 4 pi g squared times 2m delta m divided by 4g h bar. No, without the 4, because I already got rid of this. And now I want to use this delta m, which is, so this is 8 pi. I'm really not sure about my factors. 8 pi over h bar times gm times delta m, which is er over 4gm. Okay, so this is 2 pi over h bar er. Okay, so this is by how much the black hole entropy increases, because I'm dropping this guy inside the horizon. So as you see, this is not 0 as I was hand waving before, but it's actually some finite number. It depends on the energy and the radius of the object. So the radius is important. And now, in order for the generalized second law to actually hold, I want this thing to be larger than the initial entropy of the object. Okay. So this is very interesting. You're basically getting that you have some relation. So in order for the GLSL to be satisfied, you need to have this sort of inequality between the entropy of your object and its size and its mass. This is called the Becker-Stein bound. And the very interesting thing about it is that there's no G Newton appearing. So this is should be a purely QFT. You should be able to derive this in QFT because there's no gravity that appears in this relation. And okay, so this thing, I mean, there are a lot of discussion about what it means, and it's like super hand wavy. What does it really mean? So at the end of the day, people have been able to make sense of such relations using entanglement entropy. So you have to really properly define what you mean, and then you can get some inequalities. But okay, so this is some sort of interesting QFT relation, which okay, it's not this, it's an appropriately defined version of this, but that you're getting just from this, which turns out to be true if properly defined, and it actually comes from these general arguments of trying to really make sense of this generalized entropy as actually some sort of proper analog of thermodynamic entropy that increases in any process. Okay, very good. So now we're let me try to make some more comments. Okay. Of course. So this, I mean, this thing we've done it using Einstein gravity, using the area of the event horizon. Of course, if you have higher derivative corrections, you need to use the appropriate Waldo entropy. And then all these proofs, so we have to revisit all these proofs about the increase of the Wald entropy now, like relating it to all these geometric quantities. And it soon gets very, very complicated. And I mean, maybe you can do it at linear level, but non-linearly it's so there's some discussion. So there's this discussion by Aaron Wall in some paper in 1804, 10610. But yeah, it's you know, there are a lot of cases to consider, and it's not clear what the status of this law is basically at nonlinear level if you're having higher derivative corrections, but people have studied. Finally, one last thing that I think it's interesting to comment on are quantum corrections. So now if you want to consider quantum fields in your space-time, so you basically want to come up with this generalized entropy, which is now is going to be the expectation value of some area operator plus S out. Okay, so your geometry might be fluctuating. You're going to be in some state. You can take the expectation value of this area operator in that state and come up with something. This S out is supposed to represent the entanglement entropy of quantum fields across the horizon. So this entanglement entropy, the way that it's defined is that if you have well, let's say you have some pure state psi of a system, which is defined in some region here. So here you have your state psi, and then you want to consider a sub-region. So you split this into A and B. You're assuming that the Hilbert space splits into a factor associated to region A and a factor associated to region B. And then basically you want to define the reduced density matrix of A as trace over, well, the total density matrix, in this case, it's a pure state with respect to B. So you're just tracing out over everything that's happening over here. And then from this, you're getting a mixed density matrix. Then the entanglement entropy is basically of region A is trace rho log rho, rho A log rho R, maybe minus. Okay, so it's the von Neumann entropy associated to this reduced density matrix associated to this region where you've traced over B. So basically, in the case of the black hole, what you want to think of is that okay, you might have a pure state that's defined on the extended space-time. So if you want to think it's, yeah, think of Minkowski space in these Rindler coordinates. So if you consider the Minkowski vacuum, that's a pure state. However, if you're restricting yourself to the Rindler coordinates, which only describe, you know, the positive spatial axis, you're basically tracing your quantum state over everything that might be happening on the left-hand side, and that ends up being a thermal density matrix. It's totally related to, you know, Hawking radiation and all of that. Okay, what did I want to say? Anyways, so this is the analogy. You do something similar for the black hole. You're tracing over the states of fields behind the horizon, and then you're getting some contribution from the matter fields, from the entanglement entropy of the matter fields. And okay, I think maybe this was the first time, the first time that entanglement entropy was discussed was in this context, actually. Even now it's big in condensed matter and so on, but I think this was the first one. The funny thing about this entanglement entropy is that so you're doing a QFT on this you know, slightly curved space-time, but when you're having a QFT and you're chopping off over here, you're going to get divergences from the modes that oscillate very close to to the surface. And actually, you're getting something that goes to the area of the event horizon, which is your separating surface in the space-time, divided by this UV cutoff squared. Epsilon is basically the distance from the horizon where you chop off these quantum fields. So it's divergent. And then you may wonder, okay, what is this all supposed to mean? I'm having the nice black hole contribution and then this matter contribution, which is divergent. What does it mean? And it has been argued that actually this divergence, since both of these guys go like the area, you can actually absorb this divergence into a renormalization of Newton's constant. So, which obviously gets renormalized itself because it's so basically the point is that maybe none of these terms should make sense by itself, but the sum should be some nice finite number and that you can make sense of, and then okay, you can have R² corrections and one not, and then you know, subleading, and the coefficients of these R² corrections are supposed to maybe eat up the subleading corrections that you might have from the matter field. So the point is that maybe this object is a nice object to define, and basically, yeah, I think maybe one nice thing. So I don't know whether the jury is out on what this might actually mean, but what this really looks, one way to interpret this sort of relation is as saying that you might be having your, say, entanglement entropy of bulk quantum matter, this term, and then you're having a correction which is coupled, your bulk QFT is coupled to gravity, right? And somehow when you're computing this entanglement entropy, so it's actually when you're trying to do it, so I said that in order to define the state, you need to separate your Hilbert space into two pieces and blah, blah, blah. That turns out to be a very delicate issue in gauge theories and in particular in gravity, separating the Hilbert space because of gauge invariance and so on. And it has been suggested that maybe this guy is just some appropriate correction coming from some sort of edge modes that live over here that you need to introduce in order to make sense of this entanglement entropy in the presence of gravity. So there's some work in 2 dimensions in that direction, and maybe it's an interesting interpretation of what this all means. But okay, so I'll stop there. I'm over time, but if I can take 1 minute and tell you about the third law, just to be done with it. Okay, so now because we've done 3 laws and now we have the fourth, and the fourth is called the third, and it says that it's impossible by any procedure, no matter how idealized, to reduce the surface gravity K to 0 by a finite sequence of operations. So the point is usually the third law is something like the entropy should go to 0 as you send the temperature to 0. K of course is analogous to the temperature. Extremal black holes clearly have a finite horizon area, although they have 0 temperature, so that thing cannot hold. But if you're trying to take a finite temperature black hole, so finite K black hole, and make it extremal, you cannot do it in a finite sequence of operations. So what people try to do, they try to overspin, or spin to the maximum a Kerr black hole, or charge to the maximum a Rice-Norton black hole, and then well, it becomes harder and harder and harder, and then they see that they need I mean, asymptotically they can do it, but it needs an infinite set of operations, and this is the third law, that you cannot do it in a finite sequence of operations. Okay, very good. So